So today we're going to be going into Module 2.2, Graphing Logarithmic Functions and Transformations on Log Functions. So just like any other type of function, we have shifts or transformations in those functions. So when we're doing linear equations, they start with a mother graph that would go something like this. They can shift up or down the y-axis depending on our intercept. They can flip around if they're negative. We have all different ways that we can transform a linear equation. And logarithmic functions and equations are no different. The important thing to remember is that exponents and logs are the inverse of one another. So it turns out that the easiest way to graph a log function is to graph the inverse points of our exponential function. So that's what we're starting with here. Y equals 2 to the x power. So if we plug in 3 different points for x, let's use just -1, 0, and 1 because those are the easiest. So 2 to the -1 would be 1/2 because it's 1 over 2 to the first. 2 to the 0 power would be 1. Anything to the 0 power is 1. And 2 to the first, of course, would be 2. So let's do a quick graph. I'm not looking for exacts on your logarithmic functions. I'm looking that you understand how they shift, where they begin, where an asymptote might be. So that's what I'm looking for. So -1, 1/2, 0, 1, and 1, 2. This probably looks familiar to you from the section on graphing exponential functions. They will look something like that. If we're going to graph the inverse of that, that would be that we're flip-flopping our x and our y. And in our table of values, the only thing that changes is that our x and y coordinates switch positions. So we would just turn those around. 1/2, -1, 1, 0, and 2, 1. If that's confusing you, think about what that means. That means -1 equals log 2 to the 1/2, which is correct. That means 2 to the negative first power gives us 1/2. 0 equals log 2, 1. Anything to the 0 power gives us 1. Remember that circular pattern we talked about. And then 1 equals log 2, 2. 2 to the first power gives us 2. So that does make sense. We just switched our x and y coordinates. So in graphing that, we would have 1/2 and -1, 1, 0, and 2, 1. Our asymptote for this actually ends up being the y-axis. It will not go below that line. We'll come very close to that line, but not below. Okay? So think about what's another way that you can write the function of the second graph. Well, we know that the entire point of a log is that it helps us find this exponent right here. So that would be y equals log 2x. Okay? Another way you could write that is the function f of x, because you will see that too, log 2x. 2 to some power gives us y. Okay? Sorry, excuse me. 2 to the y power gives us x. Excuse me. Okay? So let's graph another one. Let's graph y equals log 4 to the x and see what that does to our graph, how it shifts it. So the easiest thing to do is then, let's change that to an exponential graph. That means that 4 to the y power gives us x. The inverse of that would be our exponential function for that would be 4 to the x equals y. Okay? So let's do a quick table for the exponential graph, and then we can flip it around and use it for our log graph. So we have x, y. Let's use -1, 0, and 1 again. 4 to the -1 would give us 1/4. 4 to the 0 gives us 1, and 4 to the first gives us 4. So the inverse of that would be 4 to the y equals x. We're just going to flip-flop our coordinates. So instead we would have 1/4 and -1, 1 and 0, and 4 and 1. Okay? So we would have 1/4, -1, so it's pretty close here, 1, 0, and 4, 1. So similar to our log 2x graph, except it's a little bit flatter, going to come down like that. Okay. All right, and last one, we're going to do the same steps. So write out the exponential equivalent, which would be the base of 1/2 to the y power equals x. If we switch those around, the inverse of that would be 1/2 to the x power equals y. Figure out what those coordinates would be, and then just turn them around. Okay, so this is the first ones we're figuring out, right? These are exponential functions. These would be our log functions. So 1/2, let's use -1, 0, 1 again. It's easiest just to use those three. You can certainly pick other numbers, but just to have a general rule of thumb that's easy to use, those are your easiest. So 1/2 to the -1 would mean we're taking the reciprocal of 1/2, which is 2, to the first power, so we would get 2. 1/2 to the 0 power is 1, and 1/2 to the first power would be 1/2. You should also recognize, hopefully, that those are the inverse results that you get from our first problem, because 1/2 is, of course, the reciprocal of 2, so you should have seen those numbers come up before. So -1, 2, 0, 1, and 1, 1/2. Approaching, but not hitting it. Okay? All right, so now let's talk about when something shifts. So that's just graphing our base log functions. Let's talk about when a log function shifts. So if we look back at our log 2 function, right? That's what this was. Log 2x is what we had down here. And our asymptote was on the y-axis. It's not going to go past that y-axis. It doesn't have the ability to do that because there's no number that you could put in for x that would result in anything going lower than 0. So that's not going to happen. Okay? So if we take our first that we had, so our graph for log of 2x looked like x and y. And let's go back and see what we had for log of 2x. So our inputs were 1/2, 1 and 2, and our outputs were -1, 0, and 1. So remember that log of x is like log of 2x plus 0. So I need that total in there to just be x. What you have to think about is what would I have to add to -1 to get 0? So within the parentheses, it's always the opposite shift. So we're going to add 1 to our x totals. So for the log of 2x minus 1, we're going to add 1 to all of our x inputs. Our y's do not change. The outputs do not change. But that x input is going to change because we have to increase each of them by 1. So we would have a negative, these don't change, but each of our x's increased by 1 because I've got to compensate for that -1 there. So that would be 3/2, 2, and 3. I just increased each of these by 1. My goal is to get whatever that value is within the parentheses just to be x. In order to do that, I have to add 1 to all of my x values. So this would then be 3/2, -1. Let's graph both just so you can see a comparison of what's going on. Let's graph the first. We'll just graph our log 2. So 1/2, -1, 1, 0, and 2, 1. That was our log of 2x graph. Now let's graph log of 2x minus 1. So we have 3/2, -1, 2, 0, and 3, 1. So what did that do to our line? It basically just shifted it all to the right by 1. And what's going to happen is now the asymptote, our asymptote, or our imaginary line that our graph cannot go past, is at x equals 1. So it makes this value here 0. You want to see whatever cancels out that number that you've gotten in there. Okay? So when it's within the parentheses, that's going to shift it horizontally by the opposite. Okay? So shift horizontally. So now let's take, here's our log 2 dx minus 1. Now let's graph this one, because now we've got something going on outside those parentheses. So let's see how that affects that. So we have, we're going to take, what's it going to affect now? Let's take what we started with here. Now it's going to decrease all of our y outputs by 3. I've got this total. Now it's going to decrease those by 3.